So people at home, it's not easy. Okay. So sorry, so this is the content structure of the presentation. Let's move forward. So let's start with a definition. According to the Oxford Dictionary, civil engineering is the design, building, and repair of roads, bridges, canals, etc. When applied to maritime hydraulics and coastal engineering, the civil engineer seeks to provide technically sound solutions to solve or to at least mitigate problems associated with the sea-land interface. For example, on your left, you see the Aveiro Lagoon example. This lagoon has a problematic issue that it closes every 3 or 4 years, and the closure of the Aveiro Lagoon promotes problems associated with the water quality. So dredging works to take out sediments from the inlet channels are a common work at this lagoon. Then at the center you see Albufeira Lagoon, which is a beach located right north in the country, and due to the configuration, at that fishing port, you have a lot of sedimentation. So boats cannot berth at that location. And then on your right, you see Covagalo Beach, so which is located downdrift of the inlet harbor of Figueira da Foz, and it experienced huge amount of coastal erosion in the last decade. The objectives of this seminar are as follows. So first, to provide a brief overview of infragravity waves, I will stress again that I hope that when you leave this session, everyone will kind of understand more or less what is infragravity wave. Then I will discuss 3 examples that I've been involved with. And finally, I will enunciate examples of open questions in the maritime hydraulics and coastal engineering field that I am to address in the future. So let's start with a brief overview of infragravity waves. So beachgoers are familiar with wind-generated waves. So all the waves that break at beaches when we go there. And this breaking is due to the limitation of the water depth. We see on this image very swell waves breaking at the beach. And most importantly, the time scale associated with these waves range from 5 seconds to 20 seconds. So imagine now that I put an oceanographic instrument somewhere in a water depth of 10 meters, either a pressure sensor or a wave gauge. What do I get? I get a signal like this. So in time, you see the sea surface fluctuations associated with wind-generated waves. So wind-generated waves, especially swell waves, tend to form groups during their propagation. This fact is well known to surfers. Usually surfers wait for the larger waves within the wave groups. So here, this is the record of the wind-generated waves. The wave group has a different time scale. So what is the wave group? It's kind of the envelope of this sea surface erosion. So if I filter and do the kind of envelope of all these waves, I get the wave group. So the time scale ranges from values between 40 seconds and 300 seconds. So we are seeing here a larger time scale than the wind-generated waves. So these are the wave groups. Then we have the wind-generated waves. They tend to be groupy when they reach the shoreline, and the envelope is the wave group. So collectively, while large wave groups will force a depression of the mean water level, this level, the mean water level, we will increase underneath the smaller wave groups. At the end, we get this kind of fluctuation with a larger time scale, which is called an infragravity wave. So more importantly, this will create a wave-like fluctuation, but with a time scale similar to the wave groups. So this kind of wave is called an infragravity wave generated by the bound wave mechanism. I will not go into details to other generation mechanisms. I will just keep here the bound wave mechanism. But the main idea is this fluctuation of the mean water level with a time scale that is larger than the generated waves. Infragravity waves associated with groups of wind generated by, and display a typical time scale of between 40 seconds and 300 seconds to say it again. So during storms, they can reach a wave height of order of magnitude 1 meter near the shoreline, order of magnitude of 1 meter. And so there are relevant coastal hazards such as extreme wave run-up, junior erosion, wave overtopping, and coastal flooding is still being explored in the both scientific and technical literature. So below you see some pictures that were taken at Costa Caparica Beach during equal storm in January, where you see a huge coastal flooding more or less near Barbados restaurants. Finally, our knowledge about infragravity waves is still advancing, even if they have been first observed by Walter Mund in 1949. Topics include generation mechanisms, propagation and transformation, and their relevance to sandy beaches, coral reefs, tidal inlets, and also seiches in harbors. For a very good overview, with almost 30 authors in 2018, you can see that document. I would like to say here an idea and to look back to this seminal paper about infragravity waves and to see the title. So the title is very simple, surf beats. So infragravity waves can also be called surf beats. And I also want to draw your attention to the abstract and to compare the abstract that we do nowadays and the abstract that they did in the 50s. So irregular oscillations of the near shore water level with periods of several minutes are correlated with fluctuations in the height and period of the incoming waves. Now, let's go to the first example. This was a work that I developed during the PhD regarding the impact of Hurricane Leslie on the Albufeira Lagoon. So Albufeira Lagoon, located more or less 20 kilometers south of Lisbon. And if we do a zoom in at that area, we see a coastal lagoon that is connected to the sea through an inlet channel. Below, you see some pictures of the inlet channel, especially on your bottom left figure. You see pictures of construction works that they are digging the inlet channel to promote the open of the inlet during Easter months. So the Albufeira Lagoon displays a seasonal cycle. So it is artificially open during Easter and closes naturally during winter months. So on your left, you see an image of the inlet close in March, and then an image of the inlet open on August 2021. This work, field observations, and this is very important, so I will repeat again. Field observations were collected during Hurricane Leslie 2018 to understand if infragravity waves were responsible to the inlet closure. So remember that during storms, infragravity waves become larger near the shoreline. So the idea here is collect field observations during Hurricane Leslie, so storm conditions, to see if these infragravity waves were really responsible to promote the inlet closure. So observations were gathered between 12th and the 15th of October 2018, and daily topographic surveys were performed at the inlet mouth with two GPS systems, more or less around the square, the red square that you see at the picture. Waves and currents and scan and sediment transport were measured based on pressure sensors, current meters, and optical backscatter sensors at the locations that you see on the image. The blue locations and the red locations. When you compare these two satellite images, you see satellite images that were taken on 12th of October and another one that was after the Hurricane Leslie. And in this area, near the inlet, you can see that this northern sand speed after the impact of Hurricane Leslie moves a lot landwards. So this was one of the effects that we will try to assess and to see highlight the contribution of infragravity waves to explain this landward movement. So based on daily topographic surveys and during the most energetic wave conditions, so between the 13th and the 14th of October, we get an accumulation close to northern sun speed that reach up to 1.5 meters. So in this picture, in this panel here, you see the topographic survey, so the elevation relative to the mean sea level along that area, and then below it's exactly the same information, but 1 day after. So you can clearly see that this northern speed moved landward, and at that area created an accumulation of 1.5 meters, 1 day to the next one. So this is the difference map. So I'm plotting the differences between the topographic survey that was taken on 14 compared to the topographic survey that was taken on the 13. And warm colors, so in red, you see sediment accumulation, and in blue, you see sediment erosion. So all across this area, from 1 day to the other day, the bottom increased 1.5 meters in height. So I'm more or less 1.80 meters, so it was more or less like this. Let's have a detailed look now to the oceanographic instruments time series. So this time series was taken at the flood delta, so a bit landward, so inside the lagoon. In the first panel, you see the water level fluctuations. On the second panel, you see flow velocities. Positive values are directed inland, so towards the lagoon. And then on the third panel, you see sediment transport rate. So the thick black line represents fluctuations associated with infragravity waves after a filtering procedure in time. Infragravity wave crests, so if you look to that time period, between 5:10 and 5:15, so within the time period of 5 minutes, you see that infragravity wave crests coincide with landward peaks in horizontal velocities. So this crest here coincide with peaks on our horizontal velocities and also with peaks on the sediment transport rate. More importantly, so the time period was 5 minutes. And when we look to the peaks, we see 4 peaks. So these peaks have a time scale of approximately 1 minute, which falls within the time scale of the infragravity waves. This is still work in progress. So a numerical modeling ICAS was performed with the morphodynamic X-Beach model. So this model is able to simulate waves, currents, sediment transport, bottom evolution in coastal areas. And on your left, you see the difference map, the observed difference map, and at the right, you see the simulated difference map exactly for the same period. So you can see some patterns. So qualitatively, the model is able to reproduce this large accumulation that takes place close to the northern speed. Although you can also detect some limitations of this morphodynamic model. So you are trying to mix everything. So you are trying to simulate waves, currents, sediment transport, and bottom evolution. And this is a very complex numerical model. So even nowadays, we still have some limitations about this kind of models. In summary, field observations were the key to understand the impact of infragravity waves on the Albufeira Lagoon in storm conditions. And the ongoing efforts to perform morphodynamic simulations show some promising results, but also the limitations associated with this kind of models. Let's go to the second example. So now we will move to Aveiro, which is north of Lisbon, along the western coastline of Portugal. So more or less here. And on your right, you see some pictures of this sandy environment. So you see city beaches backed up by vegetated dunes. And another common characteristic along this whole stretch is it has a lot of coastal structures, mainly coastal revetments and rusts. So a short phase nourishment, which is basically an underwater mount was placed at Costa Nova in 2020. The objective was to mitigate coastal erosion. So, on top, you see a common engineering solution, which is a beach nourishment. So, when you have your coastline that is eroding, you put beach nourishment there at the subaerial beach. And the expectation is that this beach nourishment will increase the beach width, but it will not stay there forever. So after a while, it will just disappear. But the other solution is to put the sand that we will put at the subaerial beach, but underwater. Of course, the construction costs associated with this intervention are much smaller than the previous one. So in this intervention, which is the largest one ever made until today in Portugal, 2.5 million cubic meters of sand were dumped in the near shore. The total cost of this intervention was about 10 million euros. The work that I will present here describes 1 year field monitoring campaign that was undertaken to understand exactly the response of the subaerial beach, so this part of the beach, to these interventions. So when you will put the underwater mount, after time it will evolve, and what you want to see is the effect that this underwater mount will have on the subaerial beach. So this is the study site. Here you see the entrance harbor. And then this coastal stretch is between Barra, which is located at north, until Vagueira, which is more or less 10 kilometers south. In between, we have Costa Nova beach. So Costa Nova is a place that also has 5 groins. So a groin field, groin 1 to 5. And this intervention was placed in the near shore at this dash line that you see here. So between groin 3 and groin 5. So field observations include bi-weekly topographic surveys that were obtained between Barra and Vagueira during low water spring tides with a DGPS system mounted on a quad bike. So, to clarify a bit this process, every 15 days I went to Aveiro beach to do a topographic survey between Barra and Vagueira with a lot of GPS systems mounted on a quad bike. And the analysis that I performed afterwards was based on the shoreline. Here, the shoreline was taken at the elevation contour 1.05 meters above mean sea level. I will not go into the details, but you can see more details about why we select this 1 meter above mean sea level elevation contour in that study. So, based on this extensive data set, 2 questions were addressed. The first one is the landward displacement of the shore face nourishment? So if the shore face nourishment goes towards the beach, the dry beach, is this linked to a seaward displacement of the shoreline? So does the shoreline goes towards the sea in the same rate or at the same distance? So this was the first question. The second one is how the subaerial beach changes, so the upper part of the beach along shore, so along the coastal stretch in response to this shore face nourishment. So this picture shows a topobathymetric profile. So the dry beach is here, the depth of closure is here. This topobathymetric profile was taken right on top of the shore face notch. So you see here there the mean water level. And so, for example, the topobathymetric profile just after the construction works was the red one, where you see here the bump associated with the shore face notch. So this profile was taken in September. In November, the green one, you see that this shore face nourishment started to move landwards after a while. So you see the difference between the red one and then the green one, and the shore face nourishment is moving landwards. If we look to March 2021, so more or less after 6 to 7 months, we see this brownish line and the top of the thematic profile, you see that the short-phase nourishment starts to get attached to the initial profile. So it's moving actually landwards. So the large short-phase nourishment landward displacement that we see on these based on these field observations was linked to a small, or at least smaller than this short displacement, smaller seaward displacement of this subaerial beach. So just to have a rough idea, is landward displacement was about 200 meters, while the subaerial beach displacement seawards was at most during the whole year just 60 meters. So this responds to the first research question. Now let's go to the second one. So what I'm presenting here is a spatial temporal evolution of the shoreline on the long-shore direction. So the first three panels show the variation in time of three parameters associated with the wave conditions. So significant wave height, peak period, and mean wave direction through time. So between July 2020 and July 2021. The bottom panel shows this special temporal evolution of the shoreline. So on the y-axis, we have longshore distance between Barra, which is located at north, and Vagueira, which is located at south. And these horizontal lines depict the position of the groin field just in front of Costa Nova. So the short-phase nourishment was put in the near shore between groin 3 and groin 5, and we can see the evolution. So warm colors, so each point corresponds to elevation contour, and warm colors indicate shoreline advance. So what I mean by shoreline advance is an increase of the beach width and the subaerial beach volume, while cold colors indicate a retreat. So every point is a specific, the elevation contour is associated 1 meter above mean sea level, and we see the special evolution. Let's look at the two main and most easily identified patterns. So the first one is within the groin field, that we mostly see warm colors even during storm conditions. So we have here very large storms during winter, and even during dead storms, the shoreline still moved and still increased in the beach width. But then, downdrift of groin 5, we see that this pattern shows and is mainly associated with cold colors. So it indicates a shoreline retreat, so a decrease of the subaerial beach volume. So, in summary, field observations suggest short-phase nourishment acted partially as a feeder environment. So, the total movement, the total landward movement of underwater short-phase nourishment does not respond to the same amount of movement of the subaerial beach in terms of beach width. And one important thing here that I also would like to highlight is the more stable behavior of the beaches that were more or less within the short-phase nourishment, especially during storm conditions. A drawback associated with this solution is, in fact, the landward shoreline displacement that we see at the downwind side. And to have a rough idea, and I think that this is important, this occurred at a distance that is similar to the length of the short-phase nourishment. So in this case, it was more or less 2 kilometers of length in short-phase nourishment. So more experience is definitely needed based on field monitoring of this type of coastal interventions. Now let's move to the third example concerning the detailed design of Barrinha de Esmoriz. We were at Aveiro, and we just go a bit to the north, to Esmoriz, where we see this coastal lagoon. So the coastal lagoon is similar to the Albufeira Lagoon. So we have a water body that is connected to the sea through an inlet channel. Here at this picture, you see an aerial view right on top of the inlet channel. And one important aspect of this Barrinha de Esmoriz is its recreational and tourism value that is highly appreciated by tourists along this area. So, unlike Albufeira Lagoon, Barrinha de Esmoriz is naturally open throughout the year. So here the problem is slightly different than Albufeira Lagoon. Its opening during summer months induces several water qualities at the nearby beaches. And so, in Proman, put forward solutions of two sandy dikes composed by a core of geobars. So the idea is, in that area, you just put two sandy dikes with a core of geobags that are connected with two barrels, here and there. So during summer months, you put sand in the inlet channel and you close the inlet to prevent water quality issues for nearby beaches. Then, after the summer period, you just go there, you take out the sand, and you let the inlet evolve naturally. So the objective is to close Barrinha de Esmoriz during summer and to open it during winter. This is a picture that was taken in November 2018. So this is the state of this solution in November 2018. So we can clearly see that we don't have any sandy dike anymore, and some of the geobags have already been pushed away due to some conditions. So after a detailed analysis, we propose the failing mechanism associated with scour and overwash. So scour in the inner part of the geobags. So here we are inside the lagoon, so scour promoted by tidal currents here at that part of the geobags, and also a combination with large waves during the storm in November 2018 that promoted some sand that was washed away from the top of the geobags. So the objectives of this detailed design project were associated with three main aspects. First, dredging works in the inner part of the lagoon. Second, rehabilitation of this sandy dike system. And third, revegetation of the nearby units. I will just focus here in this seminar about the rehabilitation of the sandy dikes. So here I present some technical drawings of the proposed solution. And the proposed solution included a scour apron on top of the existing rehabilitated and new geobags. So this is the aerial view of the study area. And we are concerned here at the inlet mouth. So if we see here this left technical drawing, this is the cross-shore profile that is along the sand dike. So this cross-shore profile is along the sand dike cross-section, right? And we see here, for example, the wave geobags that have been removed during the storm, and also these yellow ones that need to be rehabilitated, so they need to be removed and probably filled with sand again during the construction works. And here we see the final solution, which is composed of the same geobags composing the core of the sandy dike, and then we propose scour apron on top of these geobags, and also a geobag on top of the scour apron, and everything filled with sand. In summary, regarding the failure mechanism, previous knowledge that was obtained at Albufeira Lagoon, especially how the inner channels functioning, and this knowledge was obtained when research, allowed to better conceptualize the physical process that eventually have led to the failure mechanism in practice. Regarding the geobag design calculations, the most up-to-date formulations were used. And so previous knowledge obtained during research, how to search information and how to be acquainted with the most up-to-date studies was also helpful during this process. And this is an interesting case because it was even including research papers from a very large physical experiment that was made in a 3 meters long wave loom that included design calculations of these geobags. Now, I will go to some open questions that I think that are important in this area. So the maritime hydraulics and also the engineering. So the simulation of waves, currents, sediment transport, and numerical and bottom evolution, numerical model. So this is called morphodynamic models. Still constitutes a very difficult task. So here I presented the example of the Albufeira Lagoon, but I can present many other examples. So, but this is not just a research question, because this limitation has strong implications for coastal engineering practice. Because design projects can rely on morphodynamic models, and in Portugal and worldwide, coastal management authorities promote the use of beach or shore-based nourishment solutions to deal with the problem of coastal erosion. So the idea is I aim to promote the development, application, and assessment of morphodynamic models that can be used to simulate sediment-related engineering solutions. For example, nourishment, but also navigation channels. And this research line will be followed by combining field observations, numerical modeling, and physical experiments. One thing that I would also like to stress is the amazing world of sediment transport. Enough room, if we just put waves, and waves are propagating from, for example, left to right, depending on the size and depending on the wave characteristics, we can have sediment transport going from right to left. And I think that this is amazing. Like, how cool is that? So this part of the sediment transport, and our knowledge is way far from the best knowledge that we can get to develop this kind of morphodynamic models and to apply them in practice. So research or open questions that I put here includes, for example, how much and how long can coastal hazards be mitigated when using these sediment-related solutions? So this is especially important both along high energetic coastlines and when we have coastal management authorities that are concerned and promote the use of these solutions. Then, how accurate can we predict the medium-term time scale, so between 1 and 5 years of these interventions? So, for example, nourishments and navigation channels. This time scale is very difficult to predict by the morphodynamic models unless we use some very simplified models. So the idea, the question here is to look to more process-based models and how can we change them to get this medium-term time scale. Another open question that I feel that is important to also include in this seminar is how to engage students in pursuing hydraulics and water resources specialization, but civil engineering in general. So this is the open question that is also important from a university point of view. So I would like now to show two quotations from Emeritus Professor William Campaias from Queen's University, Canada. So coastal engineering was new in the 15th century. In that first, it was all about solving urgent coastal problems. So inventiveness and ingenuity were the key design ingredients. Conferences and publications where the research results are presented have become analytical enough that the presentations and the publications have become of less interest to practicing engineers. So in the process, research and design are separated. So I would like to promote as much as possible knowledge transfer between research and practice. And an open question is also, what is the best way to do that? And to close this seminar, so coastal management and engineering are exciting because of many things. So I'm also quoting Professor William Campaias. So during the last decade, I had the privilege to work with amazing knowledgeable persons, including civil engineers, oceanographers, geologists, and also biologists. So I would like to thank you all for the knowledge that I acquired during the process. Besides, no matter the profession, can you lie on the beach, swim, dive, or cruise, and tell the boss you are working. Thank you.
I will arrive to the period and ask some questions, comments, the documentation that for you guys just finished. Okay. So,
Thank you very much for your explanation of this thing. It's very important in hydraulic. And I'd like to ask you about the type of model, safety model, that combines the sedimentation problems and the water currents. Can we say something about this? What's the advice?
So this type of morphodynamic models usually are not that detailed as a CFD model that we are used to think of. So for example, CFD model will be able to simulate currents in 3D, and also turbulence, and so on and so on. And this will not be you will not be able to use a CFD to address this kind of problems in the area of maritime hydraulics and Costa Nova. So you will use process-based models, but with a time scale and spatial scale that is a bit larger than the turbulence associated with the model. So for example, these morphodynamic models use wave energy conservation equation, long wave equations to simulate the tidal flow and the currents, and then use the bottleneck of these models, which is the empirical sediment transport formations that can either be bed loads or sustainable load. And in this model, we are still using formulations that were made and obtained in the 90s. So nowadays, it's very difficult to get research funding to specifically address this problem. And without that, you cannot go any further. So I think that the key bottleneck associated with these models is due to the empirical closure equations that you use to get the standard segment and bed load segment structure.
From my experience, the sediment transport in rivers, something we also use the empirical models to simulate water transportation. And that's a problem because we have empirical models and not models. But moreover, it's the problem is that the characterization of the sediments that are being transported. Because it's not, I don't know if it's exactly the same, I guess not. In the river, the size and the granulometry of the sediment depends on the discharge that is in the river. So, and it's very difficult to characterize. So that's another problem that which is characterize the sediments that we are transporting. Can you say something about this?
Yeah.
Is this the problem? Is in the maritime and shoreline simulations, we have a much better knowledge of the sediments that are being transported or not?
Yeah, so you have some formulations associated with different grain sizes. The problem is, again, the same, because you need to have a formulation that is applicable to different grain sizes at the same time, because you are using this information for the model. But thanks for your question, because, for example, American colleagues for a very long time period, they used to put beach nourishments, so to dump beach nourishments at the Surreal beach, based on sediments that were branched from offshore pits. And usually, you are getting finer sediments than the one that are native in the sand. So there is some knowledge about how fine sediments and coarser sediments behave in terms of beach nourishment solutions. But when we are talking about morphodynamic models, I think it's well, like in river. So you have some formulations, but they were obtained for that characteristics, and in processes it's very difficult to get that characteristics. For example, just to finish my response, it will be almost impossible to put some instruments there at the inlet channel measuring sediment spots. And this is the most important part of the system because it's the most dynamic. And it will be very difficult because the system will evolve and will just cover your instrument and you will lose instrument. I've already lost instruments.
Yeah.
But this is something that you have to accept when we are talking about coastal engineering, and also when we are talking about some issues.
Yes, Maya? Yes, please.
Thanks, Diogo. This is a very interesting topic. My mind was going back in time and trying to remember in the first projects and designs how we were dealing with this problem. And there was something interesting because we were talking about initial tendencies. So the driving mechanism was the water is flowing with a certain velocity, and we will derive something like this area is prone to erosion, the other one is prone to accumulation, and we were happy with that. Because the idea is that once the things start moving, you lost control of the situation, or you started making things. So we were calling initial tendencies, and we'll be correcting our layout and design based on that. So this was the idea. Because there was this thing that we could not follow after. The morphology and what was happening was a kind of chaos, or the system is so complex that we cannot follow. Other thing is that you were showing two lagoons, the Albufeira Lagoon and the Barrinha de Esmoriz. But actually they open. One opens, as we were saying, the Barrinha de Esmoriz, and the other one is not able to open sea. And this is due to different mechanisms that are happening on the location, because in the smallest one we have on the right, you have freshwater accumulation that is enough. Actually, this is a problem because if it is closed and is not open to the sea, the guys that sit in urban areas start to suffer with some kind of inundation. On the second one, this mechanism doesn't happen because you don't have enough stream or river that fills the lagoon and reaches the opening to the sea.
It's mainly because one of them is more air dominated, while the other one is flat dominated. So naturally, one can stay throughout the year, and the other one can stay.
Yeah, I was just talking about this because we were saying that we were using on the design of this closure works that we can control due to kind of illusion on safety reasons from the other system. And so we were using lessons or learning from the other system that actually doesn't build exactly on the same line.
Yes, I understand. But for example, the currents along the inner channels will work more or less the same. So this was the process.
Thanks for explanation that question, or related to how do you see future solutions in a very dynamic environment? A lot of our engineering solutions are very static, and they're not able to cope with the dynamics of the environment. So how do you see future evolution to align more the solutions with the dynamic environment, the inherent dynamic environment of the coastal areas?
So thanks. This is of course a very challenging question, but this is the way that I see now. So there's not it will not it might not be related with the idea that I see in the next 10 years. But the way that I see now is, if you have a coastal city that is just at the sea line index space and is protected with groins and seawalls and so on, and if in your back you have a lagoon, this is very common in our lagoon, the only possibility is to still continue to increase the height. So you will not be able to do much more. But if you have some room available in the back, you can do either coastal retreats, or you can also think in trying to implement some vegetated solutions, combining with this coastal knowledge. So, for example, you have very known examples in the Netherlands where they used to have a huge growing field or just in front of a huge dike, and nowadays they are putting a sandy dike, so sand everywhere and revegetation all the dunes environments at that place. But if I'm not wrong, I think that at that location they don't have coastal or urban cities, so it will also be different place. Just a final comment on that is I think that nowadays it's also important to somehow involve the society, or at least the users that go there. Because even if your solution is technically excellent, if it's not accepted by the local community, perhaps it will not go forward. So this is also important to involve the local community somehow.
One question?
Very short question. Well, you know my background. Nothing related with these topics. First of all, congratulations, excellent presentation. Well, these are extremely complex problems. Sediments, nature, water, waves. So from the action side. Then I was wondering, for practice, engineering projects, how is this uncertainty handled when civil engineers, designers need to calculate and propose solutions? I mean, I'm used to structural materials, concrete, steel, and well, we have Eurocodes. We can quantify a probability of failure. We know service life and requirements. And how safe are these designs, and how certain are these designs?
So nowadays, it's still what Professor Tig was saying. So you indicate initial tendencies, but imagine that you want to use morphodynamic models to design these solutions. They will just help a bit in the final decision. See? So you will not use this morphodynamic model. The result of this model, unless highly calibrated and verified and so on, you will not use the end result to take the final decision. So these kind of models will just give you an idea of, for example, what is the longevity of the beach nourishment? 1 year, 2 years, 5, 10. So this is more or less the
But
question.
don't owners specify this in tenders? I want a solution for. No?
No.
This is the type of work, even some other.
Yeah, for example, we can give an example with Diogo allows me. The alga, they've been feeding regularly the so-called below the beach. And now we know how much you have to put there every year. This comes from the experience. It's about 100,000 cubic meters a year. So keep,
There is so much money involved.
you know now how long it will last feeding in time. So you can go back. So they prepare the next nourishment based on the average movement of sand, because this sand is moved into the reef from Malta towards the. So,
Okay, one more comment from Diogo.
When we are talking about breakwaters, it's a bit different. Okay? So here we are talking about and it's very important to get this knowledge to do field observations, because otherwise you will not get that every 5 years you need to, every 10 years you need to nourish all the water, for example.
Okay, Diogo, thank you very much. It was very interesting, at least from my point of view, as you can, this is, so, thank you very much for coming. And I wish you all the best for your future year. Now we have some kind of drinks and something really complex.